Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study. It's my pleasure to welcome you here this afternoon to this Institute lecture, and our speaker today is Helmut Hofer, who joined our School of Mathematics as a professor at the beginning of the academical year. At the end of this lecture, as usual, there'll be an opportunity for questions, and that will be followed by a reception in the Ford Hall Common Room, to which you're all invited. Helmut's research combines geometry and mathematical analysis. He's one of the founders of symplectic topology, and he's also made fundamental contributions to Hamiltonian mechanics, the approach to classical mechanics initiated by William Hamilton in the mid-19th century. His work has led to the creation of a whole new area of mathematics known as Hofer geometry. German by birth, Helmut did his undergraduate and graduate studies at the University of Zurich, obtaining his PhD there in 1981. He's held faculty positions at the University of Bath in England, Rutgers University, Bochum University in Germany, and the ETH in Zurich. From 1997, he was a professor at the Courant Institute at New York University, becoming Silver Professor there in 2006. And he's been a member here at the Institute for Advanced Study in 1987, 2001 and 2, and 2007. And among many other honors, Helmut was elected to the National Academy of Sciences in 2008. Today, his subject is celestial mechanics and a geometry based on area.
Thank you very much. So, before this picture goes away, let me explain this. So you have a binary star which has two stars which have the same masses and a satellite. And so the satellite will not influence these two stars. So you can write down explicitly the solutions how the stars will move, and you pick a coordinate system so that these two stars are the fixed positions. You take a rotating coordinate system and describe a small satellite with respect to the system. So then, as it turns out, there's chaos in the system, and it's demonstrated, so you had to come 10 minutes before my lecture. So if you came early, you got the full treat. Namely, one puts 4 satellites essentially at the same spot with the same velocity. Then for a long time, you only see one curve, and suddenly it starts spreading out and gets wild, and then the things are all over the place. So then let me explain this. So this reddish stuff here, Hofer's comet, is actually a computational mistake. But the rest is presumably pretty good. And it's not my calculation, it's due to Alec Jacobsen. Okay, so it's an upload on the web, so you can take any initial data where you put your 10 satellites and see what happens. So it's nice to playing around. So it ultimately always ends up in chaos. So now I have to press Alt and Tab. And then we are here. Okay, very good. Okay. So my interests lie in geometry and dynamical systems, and I use analysis to sort of bring these two things together, but I'm not going to talk about analysis here. I just will show how for certain problems this nice interplay between dynamical systems and geometry actually leads to new insights. So the first thing I want to talk about, so that you get a feeling about the kind of problems one could actually study, I will talk about celestial mechanics, then I give an application, then we become a little bit more theoretical. How should one actually see a dynamical system? Then I will introduce a geometry based on area, which is not a geometry you would easily think of, but I will do it in a gentle way, hopefully. And but all the phenomenon which you saw, this crazy picture which you saw before, that you have this kind of phenomena, can be explained that in the background there's a certain geometry, and when you want to understand it from a higher point of view, it's very useful to develop this point of view. Well, and then we bring these two things together. So now celestial mechanics is an extremely old field. One could mention many, many more people, because historians clearly know that at some point the point of view was that the Earth was in the middle and everything evolved around the Earth. That was a point of view living for a long, long time. So there was a long, long time to develop the philosophical underpinnings why that should be the case, which of course made it quite difficult then to reverse course. And of course, at some point, well, you make better observations. Well, you have a strong philosophical point of view. As a result of this, then you want to bring the things together and you develop fantastic models. Like, well, the Earth, we put the Earth here, then we put the sun here, but there are a certain number of planets which actually don't go around the Earth directly, but they go around the sun, and then everything moves around the sun. So then it takes a certain amount of time till you actually develop and see what the right point of view is by having more and more data, excluding some of the more fancier models. So the usual suspects occurring here are those who ultimately got it right, namely we have the sun and the planets go around the sun. So now I'm not talking about the history, so I will talk about mathematics, and then for me what will be important is Isaac Newton, and who found out what the laws are which govern the motion of celestial bodies. Now, while this problem itself is interesting, is from a mathematical point of view, is that over the centuries it had a tremendous impact on quite a lot of mathematical theories. And for example, if you just study two bodies moving under the influence of gravity, you can explicitly write down the solution. If you take three bodies, it's already so complicated that it generates headaches for mathematicians since 250 years, and the problem is not understood yet. It's quite amazing. At least not in full generality. So, Isaac Newton's Principia. So if you have two mass points, then they attract each other with a force proportional to 1 over the distance squared. So that's a particular law. So you have two masses here. If they are at rest, they will go to each other, and the force is given by this rule. So now celestial mechanics is, at least from my viewpoint here, is a study that you put several of those masses around. They affect each other by this law of gravity, and you see a certain amount of movement. Then a person which a mathematician whom we definitely have to mention is Poincaré. He contributed, of course, in many different directions in mathematics. But in 1880, by looking at this problem which you saw at the beginning, before my talk, what is called the restricted three-body problem, where you have two masses and you have a very small mass which you assume does not influence the other bodies, and you describe everything with respect to a rotating coordinate system, that in this system is actually chaos. What is chaos? Well, chaos is precisely the phenomenon you saw at the beginning. If you change a little bit the initial data, the long-term outcome is completely different. I mean, we are, of course, the demonstration at the beginning could also be a demonstration of the usual weather forecast, where you make measurements, which are the satellites, they are very close together, and the prediction is where they are at some point. They can be all over the place. And what you see in weather, you see also in this system. Since you can't measure accurately, the predictions in long term are usually off. So now it turns out that the fact that there is actually chaos in the system in celestial mechanics actually has some interesting applications, and I will talk about this first before we get a little bit more theoretical. So in 1968, Charles Conley, who actually made contributions in a lot of in pure mathematics, was actually thinking about how can we get a body from the Earth to the Moon by using less energy than any method known at this point was supposed or used at this point. And the interesting thing is, well, he had only some vague ideas, but this method then was implemented in 1990, in fact enhanced, so there was an additional twist to this, and it saved actually a Japanese space mission. I will tell you a little bit about this. And here, let's have a second for a commercial break. So there's a nice book by Ed Belbruno, who is actually in the audience, Fly Me to the Moon. who describes this story and some other stories how chaotic movement was used to save some space missions where something went wrong, or other space missions which were designed at some point using the more classical methods have been modified because there was still some fuel by using chaotic movements for absolutely new missions. And there's some satellite around which was started in 1978. It did already several new things which weren't anticipated at this point. It comes back in 2014 and will have another mission. And they have some problem with this thing, the battery doesn't really work. But nevertheless, so there are some interesting stories. So let me explain first what is a standard method to get to the moon. So the standard method, the idea for this comes from 1925, and it's so-called the Hohmann transfer. It's a pricey 3-day trip from the Earth to the moon. So the first thing is you usually start with a 3-step rocket, go around the Earth, so in 200-300 miles. Then you start the third step. So now you need enough velocity to get sort of approximately here. And this line here is a line where the gravity of the moon and of the Earth cancels out. So if you make it over here, then the attraction of the moon is stronger and will accelerate in this direction. Now, the thing now is, well, depending how you do this, so you can successfully crash into the moon. You can successfully go past the moon into outer space, but the trick is to actually go around the moon. But in order to achieve this, you actually have to fire the rockets again. Now, that is unfortunately very pricey. So if you manage to bring a spaceship of 1,000 pounds here, you have to burn about 250 pounds to bring it to a speed down that it's being captured, and each pound you bring over here is $1 million. So this braking here of a minute or so costs you $250 million if you have a spaceship of 1,000 pounds. So there's nothing you can do getting from here to here. That always costs money. But if you don't have to brake, you could bring much more things up there. In particular, as was planned at some point to start a space station here. You don't want to bring up material this way. It's just too expensive. So the question is there a more energy efficient method? So let me tell you the story of this, how Bel Bruno saved the Japanese. I think it's a good story from all points of view. So Bel Bruno and Charlie Conley have the same advisor as Jürgen Moser, who was a pope in dynamical systems. Jürgen Moser wrote at some point with Carl Ludwig Siegel, who was a faculty member here, a book about celestial mechanics. So from this, Bel Bruno knew Conley's idea of low energy travel, and the idea of Conley was using these chaotic possibilities which you have. So this mess, which you can basically, by choosing in a clever way initial data, you can achieve all kinds of things. That is sort of the key. Okay, so Bel Bruno has this idea, and he's working at the Jet Propulsion Laboratory where they actually make these designs. This is 1990. So he's a happy mathematician, talks to his boss, who is an engineer. So now, what happens when an engineer and a mathematician talk? Okay, engineer. Well, Ed, A, with high probability this is complete nonsense. B, if this is not nonsense, it's useless. And C, perhaps you look for another job. Now, Ed is lucky because the Japanese start their space mission. So the Japanese wanted to demonstrate that they have the technological capabilities to go to the moon. Now, what does that mean? So go to the moon means, well, it does not mean that you crash into the moon. It does not mean that you bypass the moon. What it means is you go to the moon and go several times around. That is a successful mission. So the Japanese start their mission. There's a lot of articles in the press, a lot of propaganda. It's a question of national honor. So they send 2 spaceships up which are coupled. One is supposed to be the signal station which goes around the Earth. It's designed for this, has only a certain amount of fuel. And the other thing, which has the size of a grapefruit, is supposed to go around the moon. So they bring it into low Earth orbit. The grapefruit separates, and after some time, they can't find the grapefruit anymore. So, bad. That's a tragedy in the making. So now they think, well, how can we save this space mission? So step one, they give the space mission a different name. Okay, good. So now we have to find a method by actually sending this disk to the moon. So now the disk wasn't really designed for this. And they had only little fuel in it, so they really don't find a solution. So they ask the engineers at the Jet Propulsion Laboratory. Of course, maybe it was the same engineer. A, you can crash successfully in the moon. B, you can bypass successfully the moon. And then C was presumably the ingenious answer, namely they wanted to get rid of the Japanese. Talk to Belbruno. Actually, in order to prove that Belbruno doesn't know what he's talking about, I guess. So Belbruno, however, then figures out a way, and with the amount of fuel they have, they actually manage to bring the disk to the moon. And in fact, they have to go into outer space, basically between the sun, where the gravity of the sun and the Earth is in equilibrium. You have to hit the right spot there. The moon has to be at the right spot. And then the satellite falls back, comes from behind to the moon, has essentially the same velocity and is being captured. So one shot in the right space somewhere has been captured, and you save the energy. Now, and it took about 150 days rather than the three days which the usual method takes. And I think there are now methods which take 90 days. Maybe there theoretically there could be shorter ones. Okay, so in this was the use of the chaotic dynamics in the system. And now actually a lot of space missions, in particular scientific ones, are being designed in this way, because you say, well, I'm willing to invest a lot of time, but not fuel. So if you invest time, you can actually run several space missions by just moving satellite from one place to the other, basically using no fuel, but using the gravities of the different bodies moving around in a clever way. Okay, so this was story time. And now we have to do some serious work here. So what is a dynamical system? So the theory of dynamical systems is sort of the mathematical idea, how can we actually describe a physical system? So a physical system has states, and the mathematicians would describe them as points in a space. So this here is, in this case, simple as a plane, and you should think of this as every point here would represent a state of some physical system. So in practice, in the description, a state would be described by a bunch of numbers, let's say. So at this point, we describe the different states of a system, but now, of course, we know in a physical system, the states will change over time. So why do they change? They change because there are some physical laws in the background which force the states to change over time. And how should we see this mathematically? Well, we should think of having an arrow attached to every state. And the arrow, so if here this is each point on the floor is a state, there's an arrow attached, and it says to the state, if you are here, you have to move with a velocity represented by the length of the arrow in the direction of the arrow. So I only drew, of course, a few, but you should think they are attached to each of these things. So let's assume now we have a state here. So the state looks up to the arrow, and the arrow says, well, you have to move in this direction with this state. Of course, now, when the arrow moves, what he sees immediately is a different arrow, so he always has to adjust to the state, but mathematicians have shown that there is a solution to this problem, even if the arrows move in time. So if it looks like a field and the arrows wave, there's a solution to this problem, as long as the arrows suddenly don't show in all kinds of different directions at the same point, more or less. Okay, so here you see we move along these arrows, and that is how the state would develop. but the description, of course, has not to be given by such a nice space. It could be, in fact, described by a curvy landscape, where each point would describe a state of a physical system, and the only thing you have to make sure is that the arrows are tangential to this landscape, because if an arrow shows away, then the state would move away from the space of states, which is, of course, not such a great idea. So that is how we could think of describing a physical system. We have a landscape of states. The physical law attaches an arrow to each of the states and says, state move in this direction with this and this speed. And then, given a state, we can follow a line which is called the flow line. And if we do this, we get pictures like this. Now, so here we have the space of states, and rather than drawing all the arrows, I just draw the lines how the states would evolve. Like if a state would be here, it would follow this curve here and would develop over time. So of course, this doesn't give you the information about the velocity, which we also could add to the picture, but we don't want to overload it. Then here are some interesting spots. These are rest points, yeah? Certain things from here would move over there. Now, if you would start here, you would follow this line, and then suddenly you would go in this direction. Or if you would start here, you would follow this line and go in this direction. And this is, in fact, chaos. Chaos is, if you start very close here, in long time you would end up over here. If you start here, you end down there. That is chaos in the system. And this is precisely the kind of things which you see in celestial mechanics. It's all over the place, but it's not visual. You can't really see it, but it's there. But it can be mathematically exposed. Okay, so this kind of picture which you saw now has all this stability, this instability is built in here, and this you use in this problem in celestial mechanics to bring these spaceships from one place to the other. That's the idea. Okay, so here this only explains the idea for this spaceship. So suppose here this dot and this dot are rest points. If you sit there, you wouldn't move. If you would be here, for example, if the state would be sitting on this curve, it would in time just rotate around. And suppose you want to get from here to here. Of course, if you just let nature handle this case, nothing will happen. You are at this rest point, you will stay here. So you have to cheat nature. That is why you have an engine. You have an engine to cheat nature. So you start your engine and fly over there. So now you're on the green curve. Now you let nature do the job, and it takes a long time. And if you would never use your engine again, you would follow here and go in this direction. But remember, we wanted to get over there. So at some point, you decide to start your engine again. If that would be the last time, you would actually end up over here. And then you do it twice again, and you end up there. So the idea would be to let nature do most of the job and only sometimes use your engine, but only where you have to fly very little. That would be sort of the idea. So that is, in fact, a sketch of Bell-Bruno's solution. So the disk was around here, so it was brought on such an orbit. Then it was shot in this direction here. This is about 4 to 5 moon distances towards the sun. Here, sort of gravity basically is in balance, the gravity between the effects of sun and earth. And then very gently it goes sort of down. Now the moon has to be in the right position, and then it comes with the right speed here and is being captured and stays for some time around the moon. Yeah. And the whole system is full of these things, so you can really fly around. This is like a highway system. In the real world, you don't see it, but there's a highway system up there. Okay, so let's have an intermediate summary here. Okay, so if I want to describe a physical system, then what I need is a space of states. Think of this as a geometric space, a landscape. Can be two-dimensional, can be three-dimensional, can be four-dimensional, can be infinite-dimensional. A landscape. Then each point represents a state of the system. Now, Of course, it's the art of modeling, seeing a system and writing down a good landscape, for example. You want to write down a good description, which you can use to draw conclusions which are not so obvious. Very often, these landscapes are defined very indirectly. So you even have to start exploring this landscape to understand how it actually looks like. So there are a lot of interesting things which can be said. Okay, so we have this landscape. So the next thing, we have to add a physical law, which means we add these arrows. What does it mean in practice? In practice means this landscape, each point is technically a bunch of numbers. Then there is a formula, and out of this bunch of numbers, you compute this arrow. And then you do precisely what I said at the beginning. You start with some state. You look at what your arrow is. You start moving this in the direction of this arrow. You update because you have a new arrow there, and so on. And the actual movement is you move on a flow line. And you can do this for any starting point. So you get this space, and in the space you have this set of flow lines. And if you lie on a flow line, you have to stay on this flow line. And you will move in the direction of the arrows. Yeah, so that is how you should think of a physical system. So now, for the following description, I want to simplify it a little bit. And rather than thinking continuous time, you could think about the following. Suppose I'm interested what my state is today and maybe what it's tomorrow in 24 hours, but I don't care what is in between. So you would start here, that's now, then you would move along the flow line for 24 hours and you would end up at this state here. You would disregard what happens inside. So then you can simplify this picture somewhat. Namely, you could think of a space of states and a transformation which is something like an input-output machine. You give the state of now as an input, and this machine produces an output, which is a state in 24 hours or in one time unit. If you plug in this state, let's say you end up here, or if you plug a whole set of states into this machine, you get a new set of states, which would be the states in one time unit. Yeah? So we could think about this. For example, you make a snapshot of the sky. You describe the planets, you record their position, their velocity. This evening would be one point in the state, and tomorrow, and I record it again. And then, if this would be the state today, then this machine, this computation here, would give me the state tomorrow. And if I would look at a different situation, it would tell me how that situation would look tomorrow. And the long-time behavior would, of course, be iterating this map, this input-output machine. So I take what is now, produce what is tomorrow, take this as the input, produce a new output, what is in 2 days, and so on. So now I will concentrate on this point of view, and I call this sometimes a time one map, sometimes a machine. It's also good to think of this as a machine because it turns out when you want to study these landscapes, you could study them by putting all machines on them you can think of in order to explore what this space actually is. So you construct input-output machines to explore space. And I think it's a good viewpoint as a machine. You give an input, the state now, and it puts out the state tomorrow. So it's some kind of a computing machine. Okay, so now let me talk about the geometry associated to area rather than what we all know. So let's start with what we know. So we are all living in this three-dimensional world. At least that is what we experience. There might be more dimensions, but we experience 3 dimensions. For us, it's very important to talk about distances, a length of a curve. So we are very accustomed to a geometry, which means exploring the space, but controlling at the same time additional structures we have, like being able to talk about the distance between 2 points. So take now the following, so that it fits in the previous discussion, takes the following point of view. You take this 3-dimensional space, which we have, and in this 3-dimensional space, think of every point, every location you have, as a state. Now, if I have two such states, I can talk about the distance between the states. And now think about the input-output machines which map a state to a state, but which have the additional feature that the distances between 2 points are being preserved. Well, these are the rigid motions: rotations, translations, certain reflections. So now we do something which sounds pretty much the same, but where the geometric structure we look at is not that we can talk about the distance between 2 points, but we can talk about other things. Okay, and this will be the geometry based on area. Okay, so before we do this, I want to explain a little bit why one should actually care. So of course the punchline ultimately is this geometry is in the background of what I was talking about, and actually has applications to precisely designing space missions and so on, and understanding some of the possibilities you actually have. But from a mathematical point of view, it already shows that area is something quite special. And let me explain that a little bit to you. So assume we study a quite simple system, and the simple system would be described where the states are the points in this disk with boundaries. So this disk lies in the plane and consists of all points, say, which from the origin have distance at most 1. And suppose we have an input-output machine. The only requirement which we have is if you plug in 2 close by inputs, the output should be pretty close by, which is called continuity, but don't worry too much about this. So then a spectacular result by Brouwer confirms the following. So you see, there are not perhaps too many questions you can ask, but you can ask, is there at least one state which will never change in time? Yeah? So the input is equal to the output. And in fact, the answer is, yes, there is. And that is Brouwer's fixed point theorem in 1912. If you have this input-output machine on a disk with boundary, there's always one state which is fixed. So now, what turns out is really important is that there is a boundary, and you shouldn't maybe look, if you're a mathematician, you're allowed to look at this picture, otherwise not. It might confuse you. It's wrong if you remove the boundary. So so here, in the previous example, the system was described by all points with distance at most 1 from the origin. And now, suppose you have a physical system described by all points with distance less than 1. You can ask then the same question, is there a state fixed, generally? The answer is no, because you can construct an input-output machine where the only point fixed is on the boundary, and everything is moved in this direction along the circles. So in particular, the boundary is mapped into itself, so you just remove the boundary, and the only state which is ever fixed is gone. So here is a machine which has no fixed state. It will always move. However, now, also Brouwer observed that this perhaps pathological example can never happen if you have actually machines which preserve an additional structure. So think of this. So think of a physical system described again by the disk without boundary, and suppose you have an input-output machine which has the following properties. The first property, it is reversible. That means you can run it backwards. So when can you run a machine backwards? So there are 2 requirements. If you give 2 different inputs, you should get 2 different outputs, and every possible output is actually, every possible state is the output for some state. Yeah? So when you apply this machine, every possible state is hit. Then you can actually run the machine backward. You take the state and look for the input state you need to produce that state. Yeah? So if you have a machine which you can run backwards, and it preserves area. So if you take a family of states, then of course we get a set here and we take its area, then we transform it, so we take this as input, we get this output states. If this area is the same for all possible sets of input, then he said, well, he proved, yes, then there is again a state fixed. So what broke down before is suddenly not breaking down because of an additional hypothesis that area preserved. Now, it sounds like a little bit here, but this is only the top. If you then dig further, there's a fantastic amount of things happening. It's just the first thing you see is area matters for this kind of question. It replaces something topological by some other level of by something else, and it changes the level of discussion. Now, can you generalize this to higher dimensions? How do you generalize area in dimension 2 to higher dimensions? Well, the straightforward answer would be, well, volume. So you can ask then the same questions. If I generalize it like this, are there, for example, fixed states? It turns out no. Bad generalization. There is a different generalization of area to higher dimensions, where then, in fact, some of the striking features, in fact, will survive. Okay, so how do we do this? So first we have to get a better grip on area in dimension 2. Namely, the best thing is to allow positive and negative area. So, and one should view it as a concept associated to a curve rather than a set. So if I'm in the plane and I draw this curve here, then it's a closed curve, it surrounds a piece of area, and if I'm inside, I can say this curve here is an arrow, runs around a point in the inside counterclockwise. In this case, we say we count this area positive. Now, take a curve running clockwise. Again, it surrounds some area. We say, in this case, it's a convention, we count this area negatively. So suppose you go on the same curve twice around, then you count it twice. So with 2 times the positive area, you've got twice around here, you call it twice as well. Once you did these conventions, you can associate an area to this curve here. I'm not going to the details, so you have to, but just having this convention, you can associate an area to this. For example, it cuts out this piece. Then here you have to think a little bit because, here you go counterclockwise around, and here if you cut it like this, but then you count that twice. So you have to have some correction factors in and so on and so on. But you can associate an area to an arbitrary curve. Good. Now we can actually go in higher dimensions. Namely, so at this point we have associated an area to any closed curve in the plane. The area can be positive, negative, or 0. But now we can generalize it to higher dimensions. If you're in higher dimensions, say here in the 6-dimensional space, so this here is a curve in the 6-dimensional space. So in 6 dimensions, a point, you have a coordinate system, which has, so if you are in the plane, we have a coordinate system with 2 numbers. If you're in the 3-dimensional space with 3 numbers. If you're in a 6-dimensional space, a point in the 6-dimensional standard space is described by 6 numbers. Take the first 2, take coordinate number 3 and 4 and coordinate number 5 and 6, and you can view the 6-dimensional space as a product of 3 planes. So you just take that curve, project it into the first copy of the plane, the second copy of the plane, and the third copy of the plane. These are no arbitrary curves. This has an area, this has an area, this has an area, just add it up. So now we have associated to an arbitrary curve in a 6-dimensional space an area, and you can do that also in higher dimensional spaces. Okay, so now here's this brainy space. So you can actually define this kind of structures where this is some even dimensional space, where it is possible, and I just demonstrated in a particular case, where it's possible to associate to a closed curve an area. So there are these spaces, and you can associate to a closed curve an area. So now, compare it now with what I did before. What I did before was I explained the 3-dimensional space where I can talk about the distance between 2 states, or the space we live in. It has a structure having 2 positions or 2 states. I can talk about the distance. This here is a space, and I can talk about the area associated to a closed curve. The closed curve replaces the distance between 2 points. So now you look at transformations, maps input-output machines from this space into itself, which map, of course, such a machine will map. If you feed in all the states on this curve into the machine, you get out another curve. And the only thing you require for this machine is that the area of the input loop is the same than the area of the output loop. Yeah? So before we have this three-dimensional space and the notion of distance between any 2 points, we looked at machines which preserve this. These are the rigid motions. Now we take this abstract space where we require that we can talk about the area associated to a small loop, and I gave you this standard example before, but you can define on more general spaces. And then the transformations you're interested in are those which map loops of states to loops of states with the same area. Now, that something of this kind is in the background of describing the motions of the planets or of a satellite is not obvious. You don't look into the stars and see this. So it took quite some time that this viewpoint developed. And, well, ultimately it did, and there's a lot of work happening since about 30 years in this direction, and one finds more and more things, which are actually striking consequences of having this additional structure that the area associated to a loop is being preserved. So you have this space where you can talk about the area associated to the loop, and you are interested in the input-output machines which map loops, which have certain area, loops of input states into loops of input states with the same area. So now, how many of these machines are there? It turns out it's uncountable. There are plenty of these input-output machines which are there. So it seems a priori, if you give the definition like this, you say, well, it must be really difficult to construct any of those. But there are infinitely many. It's just a lot. And the interesting thing is now when you study how you can actually construct them, what is striking is that the concept of energy naturally arises. There arises a mathematical concept of energy just from this theoretical discussion, and if you really study nature, it is actually the same energy you see there. Of course, to be honest, this field has developed in a different way that people knew that there was the area and then they found the other thing. So I'm not representing the field into the chronological order, but I think I'm representing it more from a conceptual viewpoint. So if you know what so far, and you ask, how can I create these machines, you will find that the important thing is the notion of area, so of energy. So if this here is a space of states, what is an energy? An energy is just a function which associates to a state a number. So you could always visualize this. So you have here, say, the plane, which is a space of states, and each point has an energy. So you have a landscape sitting over it, the energy landscape. So now the interesting thing which happens is, since we can talk about the area associated to small loops, there is some possible voodoo you can do to produce out of this a field of arrows. So out of energy you can produce these arrows, and when you have these arrows you can construct the flow lines. And you can even look at time-dependent energy fields. You get time-dependent families of such arrows, and you can compute the flow lines, and you get this input-output machines. And that's essentially the only way you can do it. So if you start with the geometry, you would definitely detect energy as a notion. And all this movement comes from energy. And then if you would compare it with physics, actually it's precisely the energy you see there. Like the energy, like in the planetary movement, kinetic energy plus potential energy and so on. So you would precisely detect it there as well. So now, what did we do from an abstract point of view? Well, let's be quite general now. We take a symplectic space. A symplectic space is a space where I can talk about the area associated to a closed curve. These are the objects we're looking at. And then we can look at all the machines, all the input-output machines respecting the structure. And then mathematicians know that if you study this kind of objects, transformations which preserve a structure, if there are plenty of them, they actually can tell you a lot about this space. So it's not such a crazy viewpoint. And there's some good structural machines. Namely, if you have two machines, you can build a new one. Namely, you first apply the first machine, you give an input, get an output, and use the output as an input for the second machine. Yeah? That's called composition. Any machine you can run backwards. That's called the inverse. And there's the lazy machine, the identity machine, which doesn't do anything. So what is this? Well, if you had one of the beginning classes in college or maybe even high school, that's a group. So the space of machines preserved in structure has a group. But what is interesting now, there's even an additional structure to this. Namely, so it's an infinite dimensional group. You can talk about the energy of a machine. Machines can have energies. That's actually quite interesting now, because everybody thought every machine has zero energy, which of course then would be completely uninteresting. So let's take an energy distribution here. Then what I said is, you can do some voodoo, produce these arrows, and then you can construct the flow lines, and you can construct your machine. So now, what is interesting? So first of all, if you look at energy, what is interesting? How can you measure energy? Well, you can measure energy by so let's only look at energy distributions which far outside is zero energy. So then I can look at the highest energy I see and the lowest energy I see and take the difference. That's called the oscillation. Yeah? The difference between the maximum and the minimum. Now, let's look at time-dependent energy distributions. Then you can take a time average of this. You look at the oscillation for every time, the difference between the maximal state, the maximal energy you see, and the minimal energy, and you take the time average of this. And then you can define the energy of a machine. Now, that's interesting for the following point. So if you have a machine, there are usually infinitely many different ways to construct this machine by taking completely different energy distributions. So let me start with the national debt machine here. So the national debt machine is so you take the unit disk, and now you put energy into this machine, which is 1 trillion high and negative 9 trillion down at a time. At every time. So the difference is 10 trillion. Actually, the debt is presumably 11 trillion, but 10 trillion. And you take the time average, which is 10 trillion, but you only do it in the disk. Outside, there's no energy. Now you would say there is a lot of energy in that system. However, so I have an output machine associated to this energy. And then you ask me, can I do better? Yeah, I can. I can create the same machine with, at most, energy 60. Actually, to be honest, with 16 pi. So there's a better way, but I have to use the whole space. Rather, when I put a lot of energy into the same space, you can actually create the same output by putting a lot of energy all over the place, but much less. Then there are some other interesting facts. For example, you give me any machine, and I can approximate it very well with basically machines which have no energy. That's interesting. It might indicate that there shouldn't be actually, maybe you can generate any machine with arbitrary little energy, perhaps. Then there's another thing for mathematicians. It turns out if this energy is actually positive for every machine which is not the lazy machine, then you actually have a bi-invariant metric on this group, which is an infinite dimensional, non-commutative group with a bi-invariant metric. And if you're a mathematician, you know if you have a non-compact group, even in finite dimensions, to find a bi-invariant metric on this is not the standard thing. So there are plenty of arguments you would give that the energy is always zero. Surprisingly, it is not. The energy for a machine which actually changes at least one input state to a different state has positive energy, and it satisfies some wonderful rules. Like if you run, if you compose two machines, it has an energy which can be estimated by the two other machines. And so on. There are a certain number of interesting rules. What is even interesting is that for certain spaces, the machines can be even ordered. You know, orderings for real numbers, like 3 is greater or equals to 2. And it has certain properties. It turns out these machines can be naturally ordered. So there's a positive machine, there's a machine bigger than the lazy machine, or smaller than the lazy machine, and so on. So there's a lot of interesting structures. So now, what have we achieved at this point? Well, we take a space with an additional structure, namely that we can talk about the area of loops, and we associate to this a partially ordered bi-invariant metric group. So what is this object here? This is an object where we can actually talk about distances. So we mapped a space with a geometry based on area to an infinite dimensional space with a geometry based on distance. And it turns out that a lot of these features here are being preserved when you go over here. And of course, you might not be too happy about infinite dimensional things, but the benefit is you can think very much in terms of how you grew up. You can talk about distances, lengths of curve, and it reflects a lot of the properties here. So now, this thing can be studied by a fantastic amount of theories, and has been. Gromov-Witten theory, which is sort of an offspring of string theory, can actually be used to study this, surprisingly. Then there are other theories which you can apply. So now, once you do this, and people have studied this actually for a long time, you come actually back to a deeper understanding concerning the problem I began with. Namely, when you talk about areas, then mathematicians know there are some interesting things to look at. So if you have a curve, and you can associate an area to this curve, you can ask the question, can I find a surface spanned by this curve which has an area which is precisely the area associated to this curve? It's not always true, but it's true enough. So you actually can carry this out, and what happens is you can actually solve a very old classical problem. So now I explained that classical problem, but I have to run around here. So Poincaré, who made fantastic contributions to celestial mechanics, observed in the problem which we studied here that in certain situations you can study the movements on an energy surface in the following way. So you're in a four-dimensional space, and you have an energy distribution which is time independent, and then out of this you compute the arrows and you get the flow lines, and this system consisting out of two stars and a satellite moving is such a system. So then you can prescribe an energy, and if you're in a four-dimensional space, you have an energy distribution and only look at the states having a given energy, it cuts out a three-dimensional space. A three-dimensional space called the energy surface. So now, suppose we are now in this three-dimensional energy surface. Locally, it looks like here. Looks like this space. Except now that we have all these flow lines coming along here. I don't know what happens outside, I don't care, but they come along here. And he observed that in celestial mechanics, under certain conditions, there are the closed flow lines, that is, states which are periodic. They move in space and then they start where they began. And he was able to construct a surface spanned by something of this kind, which has a property that if you look at any other flow line in space, it hits this surface in forward and backward time. Well, then you understand the whole dynamics by looking at this surface. Namely, take any state on that surface, follow the flow line till it comes back to the surface, and you get a map from the disk into itself. And you can study this and can say something about the system. And in fact, he had very deep insights to these things. Now, it turned out that everybody sort of thought that this only works in situations where you can explicitly construct it by hand. But it turns out, as consequences of all this voodoo you can actually throw on this problem, that there is actually, it's intrinsic. There is a method in the background. First of all, you have to generalize the notion of surface of section to what is called a system of surface of section. And this system is obtained by PDE methods. It's part of the structure. So you don't have to construct it by hand. And that's actually quite interesting. So here's a sort of a simple picture which I just described. So you're moving in this three-dimensional space. These are flow lines. And here, this is a trace of a periodic movement which comes out of the blackboard here, goes back in, and then closes up periodically there. You span in a surface, it will hit the screen here in this line, And then if you move the surface by pushing them forward along the flow lines, you get different surfaces, and they all exhaust the space. And the generalization produces pictures like this. And if you have this kind of pictures, for example, this, you understand where, for example, the chaos comes from. Chaos comes from things like this. And it was actually quite amazing, and it's a benefit of giving a public lecture. I actually, I work on quite abstract things. So in a public lecture, you have to think what you will talk about. So I start talking about celestial mechanics is a good topic. Then I looked a little bit at the three-body problem, restricted three-body problem, and it seems to be that this method here, which has been established for quite large classes of energy surface, might possibly be applied to this restricted three-body problem as well, which I'm working on with a visitor and a member here. And let me say that I had the chance to discuss this a little bit with Belbruno, who did a lot of computations in orbit designs, exploiting the chaos. And from a mathematical point of view, so I cannot say that we are there yet, but so we have to we can show it for certain energies and so on, but there are still some issues. But what was interesting was assuming that this kind of structures, which are intrinsically there, at least for compact energy surface, can be brought into this thing, that what you actually have is some kind of organized chaos. There's an organization in the background of the system, and assuming that you have these pictures, and you can do it, I was discussing with Belbruno. I said, well, if I have this, I should see this and this. And said, yes, I see this as well. And then he told me something, and we could explain it in the pictures. So there was actually, we did that for about 2 hours, and we were really exhausted. So it seems to be that there is, there's some evidence that some of this really very fancy stuff, which was started 250 years ago, might actually lead ultimately to really voodoo-type mathematics, at least for the outsider, to some useful things, namely to recognizing that actually the chaos one sees, for example, in the restricted three-body problem is actually somewhat organized. And of course, I'm sure engineers now love this, because if chaos is bad, but organized chaos, which you can maybe use for something, might be better. And we'll see. So my next public lecture is in a few years, so then perhaps I can say if we succeeded, and maybe I met another engineer who says, A, presumably wrong, B, if not wrong, useless. But anyway, so I will tell you my experience in a few years. That's it. Thank you. So I'm allowed to manage the questions myself. So, any questions? Give him the. Yeah, I'll be.
Given a machine, can you tell if it's without the area? Is there a simple word to test it?
Yeah, well, I mean, you can linearize the machine if you can. You can linearize machine, and then it should preserve a symplectic form, and then it does. But if it's, well, that's the best answer I can give here. But a lot of the results should be just true by preserving area, but not necessarily being differentiable, for example. Yep. Okay. Thank you very much. So I guess you have the opportunity to recover in the food hall.